Hi friends, in this session we consider various elementary functions such as exponential functions, logarithmic functions and general powers, trigonometric functions studied in calculus and define corresponding functions of a complex variable. To be specific, we define analytic functions of a complex variable set that reduce to the elementary function in calculus when z is equal to x plus I0. Here we have a definition. The exponential function for complex variable z is equal to x plus iy denoted by e raised to z is defined in terms of the real functions e raised to x, cos y and sin y as follows. E raised to z is equal to e raised to x into cos y plus I sin y. Equation number 1. We have exp set is also used instead of e raised to z, and also this y in this equation is always in radians. We have some properties of the exponential function. That is, the first one is e raised to z is equal to e raised to x plus iy, which we can write as e raised to x into e raised to iy, which is equal to e raised to x into cos y plus I sin y, and the proof is obvious. The second one is e raised to z is analytic for all z, and d by dz of e raised to z is equal to e raised to z. The function, we have the function e raised to x into cos y plus I sin y is differentiable at every z is equal to x plus iy, where y is taken in radians. When cos y and sin y are evaluated, we have a reference example in Cauchy-Riemann equation. Hence, e raised to z is analytic for all z. Also, since e raised to z is differentiable using the formula f dash of z is equal to, which is equal to uxxy plus ivx xy. For derivative with u is equal to e raised to x cos y and v is equal to e raised to x sin y, we obtain e raised to z dash is equal to, which is equal to e raised to x cos y plus I e raised to x sin y which we can write as e raised to x into cos y plus I sin y. That is, taking e raised to x outside, we can write which is equal to e raised to x into cos y plus I sin y. So, this is our what? E raised to z. That is, e raised to z dash is equal to e raised to z itself. Third property is e raised to z1 plus z2 is equal to e raised to z1 into e raised to z2. In particular, e raised to 2z, which is equal to e raised to 2z, which we can write as e raised to z whole square. Also, by mathematical induction, we can write e raised to z whole raised to n is equal to, here we have 2, that is e raised to z whole raised to n is equal to e raised to nz. That is, e raised to z1 into e raised to z2 we can write as e raised to x1 into cos y1 plus I sin y2, like that. That is, e raised to z1 into e raised to z2. This on expansion we can write e raised to x into, here we have x1, here we have z1, so here we have x1, e raised to x1 into cos y1 plus I sin y1 into, here we have a bracket, this is e raised to z1, here we have e raised to z2, that is e raised to x2 into cos y2 plus I sin y2, e raised to x2 cos y2 plus I sin y2 using definition 1. This we can write as e raised to x1 x2 into, we can take e raised to x1 e raised to x2 into what we have, cos y1 cos y2 minus cos y1 into cos y2 minus sin y1 into sin y2. That is, here we are multiplying cos y1 into cos y2 minus sin y1 into sin y2 plus, here we have I terms. What we have, in plus 1 I into sin y1 into cos y2. That is, we are taking I terms together plus cos y1 into sin y2. So, this is actually, here we have an expansion, that is, here we have cos y1 plus y2 and here it is sin y1 plus y2. So, this we can write as e raised to, here we have e raised to x into e raised to x2, we can write as e raised to x1 plus x2. So, what we have, the remaining we have cos of y1 plus y2, the next term is plus I into sin y1 plus y2. This is the expansion of sin a plus b form. So, here we have cos y1 plus y2 plus I into sin y1 plus y2. This I can write as, which is equal to e raised to x1 plus x2. So, this is actually what, this is equal to e raised to y1 plus y2. Here we have I also, y1 plus e raised to I into y1 plus y2. So, altogether this we can write as e raised to x1 plus x2 plus I into y1 plus y2. So, this is what e raised to z1 plus z2 using our definition 1. Next we have modulus of e raised to iy is equal to square root of cos square y plus sin square y, which is equal to 1. Next property. Next we have modulus of e raised to iy, which is equal to square root of cos square y plus sin square y. We know cos square plus sin square equal to 1. So, this is equal to 1. The proof is simple, that is e raised to y we can write as e raised to 0 into cos y plus I sin y, though the x term is absent. So, which is equal to cos y plus I sin y. Therefore, taking modulus of e raised to iy is equal to square root of cos square y plus sin square y, and we know cos square y plus sin square equal to 1. Next we have modulus of e raised to z is equal to e raised to x, and argument of e raised to z is equal to y plus 2 n pi. That is, modulus of e raised to iz is equal to 1. Next we have next property, e raised to 2 pi I, which is equal to 1. E raised to 2 pi I is equal to 1. Next property. This follows from the fact that we have e raised to 2 pi I. We can write it as e raised to 2 pi I can be written as e raised to 0 plus 2 pi I. Here the real part is zeros, that is e raised to 0 plus 2 pi I. This I can write as what, e raised to 0, that is here our x is equal to 0. So, e raised to 0, what we have, cos 2 pi plus I sin 2 pi. And cos 2 pi, we know cos 2 pi is equal to 1 and sin 2 pi is equal to 0. Next property, e raised to z is periodic with imaginary period 2 pi I. This follows from e raised to z plus 2 pi I is equal to e raised to z into e raised to 2 pi I, which is equal to what? E raised to z, that is e raised to 2 pi I is equal to 1. Applying mathematical induction, e raised to z plus 2n pi I is equal to e raised to z itself for n is equal to 0, 1, 2, etc. Next property we have e raised to z not equal to 0 for any value of z. This follows from the fact that e raised to z into e raised to minus z, which is equal to e raised to 0, that we know, which is equal to 1. That is e raised to z not equal to 0. Since by 5 above we have modulus of e raised to z is equal to e raised to z. And since the real valued exponential function e raised to x not equal to 0. Since fz is equal to e raised to z is a periodic function with imaginary period 2 pi I. All the values which fz is equal to e raised to z can assume are already assumed in the strip minus pi less than y less than or equal to pi. This infinite strip is called a fundamental region of e raised to z. That is, this is our x and y axis, this is the 0, 0 point. That is, here we have the infinite strip. This is the fundamental region of e raised to z. Next we have some examples. First one is simple, very simple, e raised to 1 plus I. E raised to 1 plus I is equal to, this we can write it as e raised to 1 into e raised to I. That is, which is equal to what? E raised to 1 into, that we can write as e into cos 1 plus I sin 1. This is the first one. That is e raised to I plus e raised to 1 plus I is equal to e into cos 1 plus I sin 1. Next we have to find the real part of e raised to minus 3z. E raised to minus 3z. We have to find the real part. Now we can expand, we can write this as e raised to minus 3 into, instead of x we can write x plus I. Instead of z we can write, here we can write x plus iy. So this I can write as e raised to minus 3 into x plus iy, which of course I can write e raised to minus 3x into e raised to minus 3iy, which is equal to e raised to minus 3x into, instead of e raised to minus 3i, I can write it as cos minus 3y plus I sin minus 3y. So which is equal to what? E raised to minus 3x into cos 3y minus I sin 3y. Here the real part of e raised to minus 3z is what? Here we have the real part e raised to minus 3x into cos 3y. This is the real part of e raised to minus 3z. Next example, we have to find the solution of the equations e raised to z is equal to 3. That is, e raised to z is equal to 3. Here first you take z is equal to x plus iy. Then what we have, e raised to z is equal to 3 implies what? E raised to x plus iy is equal to 3. That is, e raised to x into cos y plus I sin y is equal to 3. That is, we are taking z is equal to x plus iy. That is, e raised to x into cos y plus I sin y is equal to 3, which implies what? E raised to x into cos y is equal to 3 and e raised to x into I sin y is equal to e raised to x into sin y, that is our imaginary part, which is equal to 0. That is, here we don't have imaginary part. That is, e raised to x into cos y we get it as 3 and e raised to x into sin y is equal to 0, which implies e raised to x is equal to modulus of e raised to z, which is equal to 3, and y is equal to tan inverse 0, which is equal to plus or minus 2n pi. Y is tan inverse 0, which is equal to what? Plus or minus 2n pi, which implies x is equal to what? Ln 3, and y is equal to plus or minus 2n pi. Here ln 3 is the natural logarithm of 3 used in real calculus, which implies z is equal to x plus iy is equal to ln 3 plus or minus 2n pi. Hence, the solution of e raised to z is equal to 3 are obtained as z is equal to, here we have z is equal to ln 3 plus or minus 2n pi, where here also we have I also, 2n pi I, where this n varies from 0, 1, 2, 3, etc. Next we have to solve e raised to z is equal to 1 plus I. E raised to z is equal to 1 plus I. In order to find the numbers z is equal to x plus iy such that e raised to z is equal to 1 plus I, we write the equation, we mark it as equation number 2. This equation as noting that 1 plus I is equal to, we have square root of 1 square plus 1 square into e raised to tan inverse 1 by 1. So, we can write e raised to x into e raised to iy is equal to, but we can write which is equal to square root of 2 into tan e raised to, we have tan inverse 1 by 1, e raised to tan inverse 1 by 1. So, it is equal to e raised to I pi by 4. Mark it as equation number 3. So, e raised to x into e raised to iy is equal to root 2 into e raised to I pi by 4. We recall the fact that two non-zero complex numbers, that is z1 is equal to r1 e raised to I theta 1 and z2 is equal to r2 e raised to I theta 2 are equal if and only if r1 is equal to r2 and theta 1 is equal to theta 2 plus 2k pi, where this k is some integer, that is case may be 0, plus or minus 1, plus or minus 2, etc. Here LHS and RHS of 3 are equal if and only if what? E raised to x is equal to root 2 and what? E raised to iy is equal to, or we can write y is equal to, here e raised to x is equal to root 2 and y may be equal to pi by 4 plus 2n pi, where this n varies from 0, plus or minus 1, plus or minus 2, etc. Because we have ln e raised to x is equal to x, it follows that x is equal to ln root 2, which is equal to 1 by 2 ln 2, and y is equal to 2n plus 1 by 4 pi. Of course, n is equal to 0, 1, 2, 3, etc. And so, z is equal to, I can write z is equal to 1 by 2 ln 2 plus 2n plus, we have y is equal to 2n plus 1 by 4, 2n plus 1 by 4 pi I, and of course, this n varies from 0, 1, 2, 3, minus 1, 2, 3, etc. So, next we have logarithmic functions and its branches. The definition, the logarithmic function of a complex variable is motivated by the requirement of solving the equation e raised to w is equal to z. For w, where z is any non-zero complex number, we have some reference in the above equation examples 3 and 4. Let ln r denotes the natural logarithm of a positive real number r as used in calculus. We define the logarithmic function of a non-zero complex variable z is equal to r e raised to I theta, where this theta varies from minus pi less than theta less than or equal to pi. By means of the equation log z is equal to, this is equal to ln r plus I into theta plus 2n pi. This n varies from 0 plus or minus 1 plus or minus 2 etc. We have some remarks, that is log z is also denoted by ln z. From equation 1 it follows that log z is multiple valued with infinitely many values. All those values have the same real part, but their imaginary parts differ by integral multiples of 2 pi. If z is a non-zero complex number with exponential form z is equal to r e raised to I theta, then theta has any one of the values, that is theta is equal to theta plus 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2 etc. Where theta is equal to argument of z, that is the principal value of arg z. Hence, we have the equation 1 can be written as, we can write it as log z is equal to ln r plus I theta, equation number 2. That is log z is equal to ln mod z plus, that is log z is equal to ln mod z, that is r is mod z plus I argument of z. We have this theta is the argument of z, where here of course z not equal to 0, equation number 3. We note that if z is equal to x plus iy is a non-zero complex number, argument of z is equal to tan inverse y by x is multiple valued. However, there is one and only one value for theta lying between minus pi and pi, satisfying x equal to r cos theta and y is equal to r sin theta. This unique value of argument of z such that minus pi less than argument of z less than or equal to pi is called principal value of arg z and is denoted by arg z, capital R A, arg z. Next we have some examples. With z is equal to 1, that is z is equal to 1, we can write it as what? 1 into e raised to I 0. We have r is equal to 1 and theta is equal to 0, and using equation 1 we obtained log 1 is equal to ln 1 plus 2n pi I. This n varies from 0 plus or minus 1 plus or minus 2 etc. Being natural logarithm of 1, ln 1 is equal to 0. Hence, the above implies log 1 is equal to, this becomes 0. So, log 1 is equal to what? 2n pi I. Of course, we have the n is equal to 0 plus or minus 1 plus or minus 2 etc. Next example, that is minus 1 is a negative real number. We write it in the form minus 1 is equal to r into e raised to I theta, where r is a positive real number. That is, z is equal to, here we have z is equal to minus 1, which I can write as 1 into e raised to I pi. We have r is equal to 1 and theta is equal to pi, and using equation number 1 we obtain log of minus 1, which is equal to ln 1 plus I into pi plus 2n pi Of course, here we have n varies from 0, 1, 2, 3 etc. That is, we can write log minus 1 is equal to 2n plus 1 pi I. n plus 1 pi I, that is we are taking pi outside. Of course, this n varies from 0 plus or minus 1 plus or minus 2 etc. Next, we have principal value of log set. The principal value of log set is obtained from equation 1 when n is equal to 0 and it is denoted by this log set, capital L, principal value of log set. Thus, log set is equal to ln r plus I theta. Of course, theta lies in between minus pi less than theta less than or equal to plus pi, and also z not equal to 0, equation number 4. That is, we can write log z is equal to ln mod z plus I argument of z. Here we have capital A, argument of z. Of course, here z not equal to 0. This is equation number 5. The function log z is well defined and single valued when z not equal to 0. Log z is also denoted by what? We can also denote it by this ln z, that is capital N. This ln z is equal to, or we can write ln z is equal to what? This capital ln z plus 2 plus or minus 2n pi I. This n varies from, listen, here n varies from 1, 2, 3 etc. up to infinity. Mark it as equation number 6. So, next we have this log z defined above reduces to the usual natural logarithm in calculus when z is a positive real number r. That is, write z is equal to r e raised to I 0. Then, with the theta is equal to 0, equation number 4 gives log r is equal to, here theta is equal to 0. Here we have 0. So, we have log r is equal to ln r. So, this is the proof. That is, theta is equal to 0. Our equation number 4 reduces to log r is equal to ln r. Next, we have general powers, complex exponents. That is, when z not equal to 0 and the exponent c is a complex number, z raised to c, it is defined by means of the equation z raised to c is equal to e raised to c into log z. Log z is power to e. Mark it as equation number 1. Where this log z denotes the multiple valued logarithmic function. Powers of z are in general multiple valued. Next, we have branch, principal value and derivative of z raised to c. If z is equal to r e raised to I theta and alpha is any real number, the branch log z is equal to ln r, this is ln r plus I theta, and here r greater than 0 and alpha less than theta less than alpha plus 2 pi. That is, here theta varies from alpha to alpha plus 2 pi of the logarithmic function is single valued and analytic in the indicated region. That is, here it is x axis, y axis, this is my alpha. When that branch of log set is used, it follows that the function z raised to c, that is z raised to c, which is equal to exponential of exp of exponential of c log z, is single valued and analytic in the same domain. The derivative of such a branch of z raised to c is found by first using the chain rule to write actually d by dz of z raised to c, which I can write as, that is the derivative, that is d by dz of z raised to c. This is equal to d by dz of z raised to c, I can write it as e raised to c log z, which is equal to e raised to c, that is taking the derivative. Here I have exponential derivative is itself, that is e raised to c log z into c by z. This is equal to c into e raised to c log z by e raised to log z. Why? Because we have z is equal to e raised to log z. This I can write is equal to, write it as c into e raised to c log z by, actually it is z, we know z is equal to e raised to log z. So, I can write instead of z, I can write e raised to log z, that is which is equal to c into e into, that is c into, not e into, it is e raised to, I am taking e raised to log z to the numerator. So, it becomes e raised to c minus 1 into log z, that is taking this e raised to log z to the upper side, it becomes e raised to c minus 1 into log z, which is equal to what? C into, which is equal to c into z raised to c minus 1. That is, I have d by dz of z raised to c is equal to c into z raised to c minus 1, where mod z greater than 0 and argument of z lies in between alpha and alpha plus 2 pi. The principal value of z raised to c occurs when log z is replaced by capital log z in the definition 1, and it is given by that is principal value of z raised to z raised to c, which is equal to e raised to c log z. Here I have this log, capital log z. Third equation. Next we have to find I raised to I, and also you have to find its principal value. I raised to I. We have I raised to I is equal to e raised to I log I, and e raised to I log I can be written as e raised to I into pi by 2 plus or minus 2n pi I, that is e raised to I into pi by 2 plus or minus 2n pi I, which is equal to e raised to minus pi by 2, that is I into I, we have minus sign. So, it is minus pi by 2 plus or minus 2n pi. Here also we have I into I is minus 1, which is equal to plus or minus 2n pi, or this I can write as e raised to, I am taking minus outside, minus into 4n plus or minus 1 into pi by 2. I am taking pi by 2 outside, and it becomes e raised to minus 4n plus or minus 1 into pi by 2. All these values are real, and the principal value, that is putting n is equal to 0, we get, which is equal to e raised to minus pi by 2. Next, we have to find the principal value of minus I raised to I. Here we have to find the principal value. We know minus 1 is equal to, we can, minus I is equal to, sorry, it is minus I. Minus I is equal to 1 into e raised to I into what? Minus pi by 2. That is, I can write minus I is equal to 1 into e raised to I into minus pi by 2. That is 1 into e raised to I into minus pi by 2. The principal value of minus I raised to I is exponential I into log minus I, that is I into capital log minus I. Here we have a bracket which I can write as exponential, that is exp, I can write it as exp I into, I am taking I outside, again I have a bracket, I into ln 1 minus I pi by 2. Here also I have to close this bracket, which is equal to what? Which I can write as exponential pi by 2. So, minus I raised to I can write it as, which is equal to exponential pi by 2. That is the principal value. Here we have a minus I raised to I, exponential principal value of minus I raised to I is equal to exponential pi by 2. Next, we have an example, that is also to find the principal value of 3 raised to 3 minus I. That is 3 raised to 3 minus I. Next example. Here also we have to find the principal value. I can write 3 raised to 3 minus I as, which is equal to 3 raised to 3 into 3 raised to minus I. That is, I am splitting this. That is 3 raised to 3 into 3 raised to minus I. We know 3 raised to 3, which is equal to 27 into 3 raised to minus I. This I can write as e raised to minus I log 3. Which is equal to what? E raised to minus I log 3, I can write it as cos log 3 minus the next term I sin log 3. That is 3 raised to 3 minus I, which I can write. Here I have to find the principal value 3 raised to 3 minus I, which is equal to, it is very simple, which is equal to 27 into cos log 3 minus I sin log 3. Next also we have one more example to find the principal value, that is we have to find the principal value of z raised to 2 by 3. The principal value of z raised to 2 by 3 can be written exponential, that is exp 2 by 3 log z, which is equal to exp what? 2 by 3 ln r plus 2 by 3 I theta. Which is equal to, which I can write it as, which is equal to cube root of r square into exponential what? I into 2 theta by 3. Thus, principal value is given by, that is, I can write PV instead of principal value, that is principal value of z raised to what? 2 by 3, which is equal to cube root of r square into cos, here I have exponential I 2 theta by 3, this I can write as cos 2 theta by 3 plus the next term I into cube root of r square, the next term I have plus I into cube root of r square into of course sin theta by 2, sin 2 theta by 3. This is the principal value. This function is analytic in the domain where r greater than 0. Here of course this r is always greater than 0 and this theta lies in between minus pi and pi. So, here we have discussed exponential functions and branches and we have done so many examples. See you next time. Till then, take care.